Nice. So welcome everyone to another week's intercontinental seminar on gravity and cosmology. This week we have the pleasure to have with us here Rome and Samanta. Rome got his PhD from Saha Institute in Kolkata, India, and then he went for a couple of years to Southampton, Prague, and since 2023, 2024, he's been in Napoli, in my alma mater. And he's going to talk about stochastic gravitational wave background and its connection to simple leptogenesis models. So yeah, Roman, feel free to
Okay,
start. Thank you.
thanks Kostas for the introductions, and thanks for the invitation as well, because I'm really happy with to deliver this talk in this seminar series. So before I start my talk, I would like to say that my slides are a bit informal today, because I got to know about this seminar a few days back. So I tried to organize my slides, and also I never spoke about these two papers together. I mean, this is my first time. So please consider it as a slightly informal, and whenever you want to know anything, just stop me. Okay. So, okay, to start with, as you can see from the title, that I'm going to talk about leptogenesis and gravitational waves. So I'm not going to introduce gravitational waves, because I'm quite sure the audience is quite learned here. So, but what I would like to say first, that whichever gravitational wave signature I'm going to talk about, they are not a smoking gun signature of leptogenesis. So it's a kind of disclaimer. But the idea of this kind of research, or in general, like probing BSM models with gravitational waves. BSM means beyond the standard model of physics. It could be related to leptogenesis, it could be dark matter, axions, and whichever work you want. In most cases, you do not find a smoking gun signature. But the idea of this kind of research is the following: if you don't observe that background, you can actually exclude a significant amount of parameter space of this kind of model. So, which is good, because you can even touch some parameter space which is not accessible to any other experiments, for example, with colliders and all these things. So, with this motivation, I would like to now change my slide. So yeah, so it's basically, this is the content of my presentation. In the first few slides, I would like to show some formal slides, like introductory slides. Then in the segment, I have two segments. In the segment one, I would like to share the core idea, and segment two is basically one slide. It's a future outlook. Okay, and these are the keywords: BSM for beyond the standard model physics, GWs for gravitational waves, and U for early universe. Okay. So let me start with a very small and cute motivation, that why should we study early universe gravitational waves? And the motivation is very simple, because if you look at the picture on the left, it's a picture of our early universe. If you are at the bottom of the slide, you are very early universe, and if you are at the top of the slide, you are late universe. And depending on the dynamics of the energy densities, after inflation, there could be radiation domination, and today there is dark energy domination. So whenever we want to probe something, some high energy physics models, for example, we need some probe, right? So far the best things that we are able to make, I mean, we kind of uh, so okay, let me so yeah, so far what we have done, we built LHC to probe like high energy physics models, but unfortunately with LHC there is a limitation. You can go only up to TeV, right? But if you want to probe some models which is beyond TeV, for example, it could be the model could operate at very early universe, for example, after inflation, around grand unification scale. You need some alternative probes, right? So of course there are like lots of model buildings connected to that, and people try to obtain like indirect signatures depending on the models. But gravitational waves are super nice signatures, because they are very weakly interacting, and therefore they typically propagate without any distortion, and therefore they can carry very pure information about their origin, right? And that's why this subject has become very popular nowadays. You can see lots of paper on the archive on early universe gravitational waves physics. And so this was a theoretical motivation, and experimental motivation perhaps a bit more stronger in the sense that after the release of pulsar timing array data. So in 2016, possibly, we discovered gravitational waves for the first time by LIGO, which was astrophysical gravitational waves. But now PTA, or pulsar timing arrays like nanograv and all these things, they reported an evidence for stochastic gravitational wave background, right? And the source for this gravitational wave background is not known yet, but this nanograph collaboration, they basically analyzed lots of early universe models compared to the most natural astrophysical sources in this PTA frequency range, which is supermassive black holes, and they found stronger evidence for uh, for for many early universe gravitational wave sources. So this is basically motivated lots of people to write more, to work on this subject more. And not only LIGO and PTA, there are lots of other detectors like Cosmic Explorer, LISA, and DAISYGO, BBO, and all these things. So the idea is, whenever you have like this multiple detector, you can do a multi-frequency gravitational wave study. For example, if you have a gravitational wave spectrum like this, where on the x-axis we have frequency, and on the y-axis we have energy density. So this is not exactly the energy density, it's energy density normalized to the critical energy density per logarithmic frequency interval. So this plot shows that, let's say your model can explain the PTA, and the spectrum also passes through the LISA. Therefore, if the LISA doesn't observe the signal, your model or some parameter space of your model will be ruled out. So this is a nice thing about multi-frequency gravitational waves study, and therefore we can do lots of early universe modeling, keeping in mind this opportunity of testing our models with multiple detectors. Okay. So there could be many sources of early universe gravitational waves, actually. Not many, I mean several sources. The first and foremost is like superstar of cosmology, which is inflation. And then from particle physics side, we can have fast order phase transition topological defects, which is basically a topic of my talk. And then there could be compact objects like primordial black holes and all these things. So our work is based on two sources. One is cosmic strings, which is also a topological defect. And also there's a new gravitational wave source that people are trying to discuss nowadays, which is early structure formations. I will explain that in a bit. But before that, let me also set up the premise for my talk, which is based on an idea of cosmic tracers. So this tracers is basically finding a configuration in the BSM models with which you can reduce the parameter degeneracies of your model while reconstructing the model parameters from gravitational wave signal. Okay, so I'll explain what is this. But before that, let me tell you that I'm going to talk about two different sources. One is cosmic strings, and another one is early structures. For cosmic strings, I will talk about a closed model in the sense that in that particular model, we have the tracers and also we have the gravitational wave source. But for the structure formation case, we have a model, but it's an open model. I mean, we have the tracers. For that configuration, we can reduce the parameter degeneracies, but to generate gravitational waves, we need some external sources. Okay. So based on this idea, let me now proceed to the next slide. So okay, these are some preliminaries, which is very obvious to the audience, to the current audience. So I made these slides for a colloquium talk, actually. But the crucial element in this slide is this equation, which is the gravitational wave propagation equation, and the most important part is on the right hand side, which is the anisotropic stress. It's basically source term of gravitational wave. So whichever source you have, you compute this anisotropic stress, and then you compute the energy density from these tensor perturbations. Okay, so okay, let me now talk a little bit about cosmic tracers. For example, let's say you have a gravitational wave spectrum like this. It is coming from some source, let's say phase transitions. Okay, so actually whenever we try to build some models, some BSM models, and try to obtain a gravitational wave signature, including phase transition dynamics as a source for gravitational waves in those models. So if you observe the signal, it's very difficult to tell from which BSM models is coming, right? Because this property is basically the properties of the phase transition, not so properties of the model itself. You can of course control the amplitude and also the peak position of the position of these peak frequencies, but in general, I mean, there are lots of model degenesis. For example, you can do a model A to reproduce the signal, you can do model B, and you can do infinite number of models. Okay, so you can partially, of course, mitigate this degeneracies. For example, you can do a parameter inference or Bayesian analysis to compute the base factor and to see which model is performing better. And secondly, you can do a multi-source modeling. For example, you can construct in a model that you have an extra source and that can give an extra peak somewhere, and therefore you can claim that my model has 2 peak, 3 peak, 4 peak models. Lots of papers are like that. But to construct economically those kind of models is it's not trivial. I mean, even if you forget this model degeneracy, there in this kind of research area, I mean, when you try to try to test the BSM models with gravitational waves, there is something called parameter degeneracies. For example, if you want to track some parameter in your model, which could be some scales of your physics, it could be some coupling or whatever. Let's say it has some range 1 to 10, and you want to map this some point of this red arrow to this peak frequency. Even in most cases, I mean, that is not trivial to do. Okay, simply because the number of spectral features we have in the gravitational wave spectrum from a given source is not so model parameter dependent. It's basically the properties of the source. So, but if you find some configurations or some parameter space in the model, in which you can build the tracers, you can reduce the parameter degeneracies. For example, now from 1 to 10, you can make it to 1 to 4. Therefore, if you don't observe this peak here, you can exclude the rest of the parameter space. So this is very so the main point is, in a given BSM models, in general, you need to find a parameter space where the parameters are mostly sensitive to gravitational waves or spectral features, and that particular parameter space is basically a high quality parameter space for gravitational waves searches, not the entire parameter space. So with this in mind, we tried to study several BSM models, and in this talk I would like to focus on cosmic tracers, and I would like to show that in simple leptogenesis model you can build these tracers and actually an early matter domination, because in general after inflation we consider radiation, then matter, then dark energy, but in some cases you can also have early matter domination before the actual radiation domination, and that early matter domination can act as a cosmic tracers. And if you can find those tracers in models, for example in our case in leptogenesis models, you can map leptogenesis parameters very sharply to gravitational waves spectrum features. And in most cases, in leptogenesis case, we actually want to know what is the scale of leptogenesis. As I would like to show that in our case, we can map the leptogenesis scale, which is basically, I would show that is right-handed neutrino mass to the spectral features of the gravitational waves, which could be peak frequencies, which could be some spectral break or something like that. Okay. Okay, now let me introduce the gravitational wave stuff. Okay, so as I said, so my talk is about two sources. The first one is cosmic strings, and the second one is the early structures. So before I introduce cosmic strings, let me start with a simple defect, which is domain walls. Okay, so then we can trivially generalize the discussion to cosmic strings. So you can start with a potential like this, which has Z2 symmetry, where phi is the field and V is the vacuum expectation value of the potential. And the potential would look like this, right? So at very high temperature, due to the finite temperature correction, initially the phi sits at 0. And when the phase transition happens, it can either go to plus vacuum or minus vacuum. So for what we want to know specifically in the context of gravitational waves, how this phi behaves in the position space or configuration space, right? So for that, we need to solve this equation of motion for phi. So this equation of motion is in some rescale coordinate, but that is not important. The important thing is when you solve this equation and take the static solution in one dimension, you will get a profile like this, where on the x-axis or on the horizontal axis we have the position space variable, which I consider to be z or z, and on the vertical axis we have phi. So from this picture, as you can see, that for very large values of z, phi would be at a plus vacuum, and for negative large values of z, phi would be at minus vacuum. And when when we are approaching towards z equals to 0, the phi is passing through 0. And when phi is 0, when the phi is at the top of the potential, and what the top of the potential means, the phi is very energetic, right? So all of a sudden, in a seemingly ordered configurations, when this phase transition happens, due to this peculiar symmetry of the potential, which is Z2 in this case, you can have an energy bump around Z equals to 0. So this is a defect of the system, right? And because these kind of scalar field potentials at the top of the potentials are extremely energetic, and therefore they are ideal sources of gravitational waves. So these defects are generally characterized by two parameters mostly. The first one is tension, which is related to the vacuum expectation value, this V. And for domain wall case, it goes as V to the 3. And the second one is the width or thickness of the defect, how thick these defects are, which is inversely proportional to the vacuum expectation value. So possibly would like to understand these things in 2D. So, okay, let me put 1D here and 2D. So for 2D, I think to obtain exact solution, it is not possible. So for that, you need to do a lattice computation. Okay. So, I mean, once you do solve this equation in lattice, in 2D, what you will see this kind of structure, that at some point you will have a minus vacuum in some region of space, and in some region of space you have plus vacuum, right? So, and these vacuums are separated by some boundaries. In 2D you can call them domain boundaries. Now let us come to the much more realistic dimension, which is 3D. So once again, you do a 3D lattice computation. What you will see a structure like this. Because these structures, a topology of wall, we can call them domain walls, right? And once again, these domain walls are extremely energetic because around this, I mean, on this surface, this phi is typically at the top of the potential, and therefore they are ideal sources of of gravitational waves. And physically, what happens? This equation also have a time evolution, right? So once you switch on the time, you can see the movement. Actually, these guys are moving, and during their motion they generate lots of anisotropic stress, and therefore they generate gravitational waves. Actually, a typical movement will look like this. So initially you form very like close walls, then it starts to become a small wall. This solution is called scaling solution. I'm not going into the detail of that scaling regime of domain wall, but what the main message that because of their bulk motion you generate anisotropic stress. So in most cases in early universe gravitational wave sources, this is the primary mechanism to generate gravitational waves with energetic objects. Okay. So a little bit about lattice computation. So actually this slide has nothing to do with my talk. I just wanted to advertise a lattice interface that we are trying to build in Python language. So that's why I put these slides. So basically, this kind of simulations are a little bit expensive. What you need to do, you need to do parallel computations. You need to you need to first construct this simulation box and make it, slice it, and then send all the slices to different nodes of your clusters and all these things. But finally, what you do, you basically solve this spectral function to compute the gravitational waves. Okay. So, okay. So, so having understood the domain wall case, which is consequences of very simple potential having Z2 symmetry. Now let us skip the simulation stuff and let us directly go to the cosmic string case. So instead of Z2 symmetry, now if you have a U1 vacuum, instead of wall, you form a string-like object. Okay, and you can basically solve these anisotropic stress equations for these long strings to compute the gravitational wave. But unfortunately, from long strings, the amount of gravitational waves you get is very small in general. So, but an interesting things happen. I mean, when this when these long strings interact, they can chop up loops, and it turns out these loops are basically the dominant sources of gravitational waves. Okay, and depending on which energy density, in which era you form the loop, and then you will have a different different shape of gravitational waves. For example, there could be some loops which are formed in radiation domination, and also they decay in the radiation domination. This, for example, this YOLO loop. For that, you will get this spectrum like this YOLO spectrum. First, it goes. This variation is up to the 3/2, and then it becomes flat. Okay, there could be some loops which are formed in radiation. This green stuff, green loops, and decay in matter. Okay, they will give you this green peak, low frequency peak. And then there could be some loops which are formed only in matter domination and decay in the matter domination. They will give subdominant contributions like this. Okay, but the crucial idea, so this is the standard cosmology, that after inflation we have radiation, then matter, then dark energy. Dark energy is not relevant in this talk, so I skipped it. But the crucial point is this gravitational waves spectrum is extremely, particularly the high frequency part of this gravitational wave spectrum is extremely sensitive to the cosmology. For example, instead of radiation, now you have something else. For example, it could be early matter domination, it could be some vacuum energy, it could be some kination type of scenarios, and depending on those scenarios, we will get the spectral features like this. Okay, it's some spectral features here. This is basically a window to test new physics with cosmic strings. For example, if you have an early matter domination, the spectrum will fall. If you have a kination type of scenarios for which you have equation of state parameter 1, then it will increase. And if you have some interaction with primordial black holes and all these things, you will get some wiggly features and all this crazy stuff. Okay, but the basic idea for the gravitational wave computation from cosmic strings is that you need to solve these equations numerically. Okay, and the crucial parameters for this computation is the first one, which is an expansion parameter, and the second one is the loop number density. Okay, so you need to solve this equation, which is called velocity dependent one scale model, to compute the gravitational wave spectrum. So now if you have a different equation of state, so typically you change this expansion parameter and also this A beta, which is loop production efficiencies from long strings. They will also be different. For early matter domination, you will get reduced amount of A beta and the spectrum will fall, and at high frequency. If you have something else, it might increase, and all these things. Okay, so in this papers, we did different kind of cosmological scenarios to see which kind of spectral features we get. Okay, so but the point in today's talk is I'm going to talk about early matter domination, and to find if we can embed this setup in very simple leptogenesis models, because generally leptogenesis are not tested with gravitational waves. It's a very new subject which are kind of and many people are trying to work on. So we also have some work on that. So that's why I would like to promote this subject a bit. So basically, the idea is the following. Let's say you have a model, and in that model you have a string solution. For example, you want symmetry, and you break that U1 symmetry, you get strings. If in the same model you can generate the early matter domination, right? Then the model parameter will be imprinted on the gravitational wave spectrum like this, because when the spectrum will break, that will depend on when the early matter domination will end, and because within the same model you are creating this early matter dominated epoch, the model parameter is sensitive to Tn, and therefore this model parameter will get connected to a break. Therefore, if you don't observe this a break at the desired position, then your model parameter, if you can map it properly to to the spectral break would be excluded, or you can test your model parameter. As I would like to show that in this way you can test the scale of leptogenesis, or in other words, in very simple leptogenesis model, this early matter domination can track the leptogenesis scale, and within the same model we can also have cosmic strings. Okay, so this is the first setup that I'm going to embed in a leptogenesis model, and the second setup is induced gravitational waves, which is a very popular topic, which is known generally as scalar induced gravitational waves. So basically, for scalar induced gravitational waves, you generate gravitational waves at the second order with these, depending on which kind of scalar power spectrum you choose, and mostly the studies are done in the linear regime. But if you have an early matter dominated era, okay, the sub-horizon density perturbation can grow because it goes as the scale factor, and therefore at some point the scale will go nonlinear, and this nonlinear regime is not so well explored actually. And recently there is a simulation by these guys, and we wrote the paper after this paper came, because we thought that this result is very interesting, and in some sense it was possibly, this was the one of the first simulations for nonlinear regime of induced gravitational waves computation. So the thing is, when this the scale goes nonlinear, it's not solvable analytically, because you will form structures and halos, and because of those complicated bulk motion of those halos, you will generate gravitational waves. Okay, so these paper performed an n-body simulation, so combined with the lattice framework, and they computed the gravitational wave background in the nonlinear regime. And a typical formula for this nonlinear gravitational wave background from the nonlinear regime would be like this, where it goes as k to the 3/2, where k is basically the frequency. Yes, and also it is basically limited within these two cutoff frequencies, where k high is basically the peak frequency, and the k low is possibly is due to the simulation resolution or something like that. But the crucial point is the following. So far the computation was limited to the linear regime, which is this black spectrum. They also reproduced this the analytical result of I think this result was by Mehta at all. I'm sorry, I forgot to put the reference here. And this is the nonlinear regime gravitational waves. And if you look, you have enhancement of the order of 10 to the 4 or something like that, which is kind of huge. First of all, the enhancement, because of this enhancement, it basically increase the observational prospect. And the second one, you also covered the high frequency range of these gravitational waves. So this formula, actually you can fit this part of the spectrum, and in terms of f, you can simplify the previous formulas like this. So with this formula, we typically fit this part of the spectrum. Okay, and what I'm going to discuss, this part of the spectrum. And if you see, this f high is now dependent on this t decay, and this t decay is basically when the matter domination end. And once again, because this peak frequency is basically related to the t decay, and what I have said previously, that I'm going to connect the BSM model parameters with this t decay, with the parameters which I want to track, and therefore this f high or peak frequency will be related to the model parameters. And the context of leptogenesis model, once again, we can relate this f high to the scale of leptogenesis. Okay. So so this was the setup. Now I'm going to discuss the leptogenesis model and include this setup in the leptogenesis scenarios. Okay, so what is leptogenesis? Leptogenesis is basically a process. It's a very well-known topic. It's basically a process to create baryon asymmetry of the universe, and pioneered by these two gentlemen, Fukugida and Yanagida. So basically, you create a lepton asymmetry, and there could be many channels to create a lepton asymmetry. For example, you can use a PBH, gravitational interactions and heavy neutrinos, and possibly this heavy neutrino creating lepton numbers with heavy neutrinos is much more popular than other mechanisms. And then with sphalerone you convert this lepton to baryon and you generate baryon asymmetry. Okay, so why this heavy neutrino leptogenesis with heavy neutrino is popular? Because heavy neutrinos are in general introduced within the standard model to explain neutrino masses, light neutrino masses that we kind of established with neutrino oscillation data. Okay, so apart from generating light neutrino masses with seesaw mechanism, these heavy neutrinos can CP asymmetrically decays to produce this lepton number. So basically, the decay would look like this: that you have these heavy neutrinos, which is helping you to generate light neutron masses, and then it is also decaying CP asymmetrically to lepton and Higgs. So this is basically the CP asymmetry parameter, some complicated expression. But at the end, what you need to solve, you need to solve these two equations. The first one is how you populate the heavy neutrinos in the early universe with some interactions. It could be some scattering, it could be inverse decay, and then how this neutrino decays to leptons. Okay, the first term is basically proportional to the CP asymmetry parameter, and the second term is called washout term, because this in the early universe, the inverse process is also active. Therefore, lepton and Higgs can also reproduce right-handed neutrinos, and therefore they can erase some part of the lepton asymmetry, right? And so this is basically washout. So when these all the washout processes are over, you generate typically lepton asymmetry, then you do baryogenesis stuff. But typically at the scale at which this freezing mechanism or this freezing of lepton asymmetry happens, it's around z equals to 1, or a temperature which is of the order of capital M, where capital M is the mass of the heavy neutrinos. So whenever we want to track the scale of leptogenesis, indirectly we mean, in general, in the context of thermal leptogenesis, we would like to track this parameter M, which is basically the mass of the heavy neutrinos. Okay, so given a model, now if I can relate this mass of the heavy neutrinos, in our discussion we want to relate, we want to track this scale of leptogenesis, because it could be at very high scale which is not accessible to collider. So in our context we would like to connect it to the early matter dominated domination scenarios. But before that, let me talk a little bit about okay, let me some previous how people try to probe leptogenesis. For example, in the CP asymmetry parameter, you have this parameter called MD, which is Dirac neutrino mass matrix, and you can express this Dirac neutrino mass matrix in terms of U is the neutrino mixing matrix that we observe in the experiments, and this omega is a complex orthogonal matrix. This dm is this light neutrino mass matrix, and mr is basically the heavy neutrino masses. Okay, so you can make the leptogenesis sensitive to the neutrino mixing parameter, because it appears in U. This MD is a function of U, and then this MD is appearing in the CP asymmetry parameter here, and also in this equation. So this is so far, I mean, this is how so far people tried to probe leptogenesis, finding some signatures in neutrino oscillation experiments. But now we are trying to do some gravitational wave stuff, right? So once again, depending on scale, I mean, depending on the several mechanisms or of leptogenesis, there could be different scale at which this process can happen. For example, there are examples of low scale leptogenesis, which is in this GeV range, and once you have like GeV scale neutrinos, you can probe with this collider experiments and all these things. But if you have leptogenesis which is operating at very high scales, you do not have any probe, right? And for that we want to do this GW stuff. Okay, so once again, the basic motivation in our in this model to generate an early matter domination in the leptogenesis Lagrangian. So the first one is the Dirac neutrino mass term. It can generate Dirac neutrino mass term. The second is basically the mass term for the right-handed neutrinos, and this one is Potrel coupling. Okay, so what I introduce in this Lagrangian extra field. this phi, which is giving mass to the right-handed neutrinos. Okay, and I will assume that this Lagrangian has U1 symmetry. Actually, you don't need to assume. You can get this Lagrangian from many well-motivated GATT scenarios. Okay, so now what I would like to show that this phi, this new scalar field phi, which is basically making these right-handed neutrinos massive, they can provide you matter domination. Okay, so first what happens at a very high temperature. So we are going to consider very simple scenarios of second order phase transition. And so at very high temperature, the scalar field basically sits at the top of the potential, and when it comes down to the bottom of the potential, it basically oscillates. Okay, and and oscillates in a quadratic potential, and therefore once you have an oscillation of scalar field in the quadratic potential, you can show that equation of state is basically is basically a matter like equation of state, where you get pressure equals to 0. Okay, and the lifetime of this oscillation, or the duration of this early matter domination, now should be related to the neutrino parameters or the leptogenesis parameters, because as I said that I want to use EMD or early matter domination as tracers for leptogenesis that can see the scale of leptogenesis. Therefore, we need to consider the decay channel of this scalar field in a way that it can be related to the neutrino parameters. Okay, so before that, let me show you this picture that initially the phi sits at 0 due to the finite temperature correction, and as the temperature goes down, at some point you will get a 2D degenerate vacuum, which happens at critical temperature Tc, and this G prime is basically gauge coupling of our model, because we are giving a U1 gauge symmetry to this Lagrangian, and at some point this phi will come to the vacuum and try to oscillate to give you matter domination. Okay, and this is basically the most central part of my talk, that this phi would decay to standard model Higgs, and this decay rate is basically connected to the neutrino parameters. Okay, and therefore the lifetime or duration of the matter domination, or the end of the matter domination, is connected to the neutrino parameters, and in particular the mass of the heavy neutrinos. And as I said before, that the mass of the heavy neutrinos is basically the scale of thermal leptogenesis, and therefore the early duration of the early matter domination is connected to the scale of the thermal leptogenesis. Okay, so you can solve this equation to see like how much matter domination you get. You can, depending on the parameters, you can get like small duration matter domination, long duration matter domination, and then try to compute the gravitational wave spectrums. But before that, let me show you two slides, because in our initial draft we did not include these two effects that we learned from a referee of our paper, that we should check it. And we recently checked it, that the referee complained that possibly our oscillation might get damped by the friction effect of this phi. So you can have this friction term like this, where yn is basically the Yukawa coupling and g is the gauge coupling, and you can solve the scalar field equation of motion with this friction term. But essentially what we got, that for our parameter space for which we got the matter domination, actually this term is not relevant. So if you are at this red parameter space, your motion will be damped, over damped region, and you are in the green parameter space, then you are in the under damped region. And our model parameter space is this deep green region. Just to give an analogy with electroweak phase transition, because this scenario is very similar to standard model Higgs. So if you increase this coupling strength to the order of like W bosons or top coupling, you can generate this over damped region. Actually, I mean, we were able to reproduce the electric phase transition scenarios, but in our case this damping is not so relevant. And the other one is parametric resonance, because whenever you have this oscillating stuff, it can produce particles. Okay, so in general, this phi, the newly introduced, it has coupling to neutrinos, gauge bosons, and also standard model Higgs. But we can show that for neutrinos, the coupling, for neutrinos and gauge bosons, in principle, we can have like a broad parametric resonance. I mean, the possibility of parametric resonance is high. I mean, generally, the strength of the parametric resonance is quantified by this parameter called Q. If this Q is greater than 1, then we will have a broad parametric resonance. And if the Q is less than 1, then we can have narrow parametric resonance, which is basically not so important for an expanding universe scenario. But fortunately, in our case, the mass of the heavy neutrinos and gauge bosons are much more heavier than this scalar field, and therefore the most violent burst production is absent in our case, and therefore we do not expect significant fragmentation of this oscillation through parametric resonance, because we are in the super heavy daughter regime. In this regime, the number of particles that you generate is exponentially suppressed by Landau-Jenner factor. Okay, but we did not perform the lattice computations yet for this parametric resonance in our model, because to compute the energy draining precisely, we need to do a lattice computation. But we expect some fraction of energy to be drained by parametric resonance, because at large amplitude, when this phi will oscillate with large amplitude, at some point you will get some energy draining. Okay, so yeah, but we do not expect that a significant amount of energy will be drained with parametric resonance in our model. Just to give you a quick summary, that I have a scenario, a timeline like this, that after inflation ends, we have radiation domination, then we have a scalar field which is oscillating. Okay, and we have Lagrangian with U1 symmetry. So basically Leptogenesis Lagrangian with U1 symmetry that can produce strings. Okay, and because this oscillation is happening in a quadratic potential, it can give you early matter domination, and the lifetime of this early matter domination is basically controlled by the neutrino parameters in our model, and that's why this early matter domination can track the scale or the mass of the heavy neutrinos, and therefore we call EMD as a tracers for leptogenesis. And as a consequence, you will get some spectral features of the gravitational wave radiation from cosmic strings, and also some scalar induced gravitational waves. So we also studied another source of gravitational waves, which I'm not going to discuss in these presentations, but let me go directly to the results. Okay, so this is the typical parameter space that we obtained, where on the x-axis we have Mn, which is again the scale of leptogenesis, and on the y-axis we have Fn, which is basically the U-Cow coupling. Okay, and these are constrained. This parameter space is constrained by several model constraints. For example, we want this decay channel to dominate as the dominant decay channel for this phi. So we computed many other decay channels and then put constraint on the model. And also this decay should happen before BBN, otherwise you are going to spoil the BBN, big bang nucleosynthesis. And the second so some constraint like that. Actually, I don't remember all the constraint right now. Okay, so this is a typical parameter space for the gauge coupling value 10 to the -2. Okay, so so having having obtained a parameter space in which we can have a matter domination in leptogenesis model, now we can study the cosmic string spectrum. As we said, as we studied before, that if you have matter domination, then the plateau for these cosmic strings, for plateau of these gravitational waves from cosmic strings breaks at certain point. Then depending on the model parameters, you basically break this plateau, right? And this break is extremely sensitive to the mass of the heavy neutrinos. And in this way, if you don't observe this break, you can rule out like some scales of leptogenesis in this kind of model. That is the basic idea of this scenario. Okay, so this is on the left side, on the vertical axis we plotted this plateau. Okay, and on the y-axis we have this f decay. So f decay is basically this turnover frequencies, and in this U1 gut motivated U1 model, basically we defined this window as the the gravitational waves window of leptogenesis, for in which you can track leptogenesis scale quite precisely. Okay, so and the plot on the right hand side, I think it's much more interesting. Because these different color regions are for different masses of the heavy neutrinos. This yellow is for 10 to the 10 GeV, this red is for 10 to the 9 GeV, and this green is for 10 to the 8 GeV. Okay, but so this parameter space is after you scan all the parameters, including the gauge coupling. But the crucial point is the tip of the parameter space is for large gauge coupling. Okay, and in general, whenever you have a GATT motivated U1 symmetry and you want to embed it in GATT models, you need a very large gauge coupling from a unification perspective. So if you have a like GATT motivated model or large gauge coupling model, then the mapping of this leptogenesis scale to this break frequency is extremely sharp. Because it's at the top of at the tip of this parameter space. Okay, so for example, if you don't observe break here, then in this class of model leptogenesis, which happens at scale around 10 to the 10 GeV, it will be excluded. So that is basically the idea of this cosmic string paper. Okay, so once again, let me show some results for the induced gravitational waves case, because initially we wrote this cosmic strings paper first, but then when we got to know about the simulation paper of induced gravitational waves, which are generated from the early structures basically. So you can once again because this f high was basically connected to t decays, and therefore in our case the leptogenesis scale, you can relate the leptogenesis scale to the peak frequencies of these induced gravitational waves. Okay, so once again these plots are for different leptogenesis mass, right neutrino masses, or in other words for different leptogenesis scales. Okay, so this is the central plot possibly in our paper, that these are some island of parameter space that you are going to get. And once again these different color regimes are for different masses for right-handed neutrinos or different scales of leptogenesis. Therefore, if you don't observe these peak frequencies here, you can exclude this parameter regime. But the one crucial point I would like to mention, that in the structure formation case, we assume that there is some external scalar perturbations, AS parameter, which we assume to be scale invariant. So we could not generate the scalar perturbations from our model itself. So we had to rely on on the fact that it's coming from somewhere, for example, inflation. So these are so AS is a free parameter in our models, and the amplitude of these gravitational waves depends on the AS parameter, or the amplitude of the scalar perturbation parameter. Okay, so once again, if you do a mapping to particular frequencies, for example, if you do a mapping to for example, like the frequency, the peak frequency, if you take the peak frequency to be 1 Hz, then the mapping is extremely sharp for large gauge coupling values. I mean, mapping means mapping to the frequency, mapping of M to the frequency. Okay, and then if you come to the Lisa range, then it becomes a slightly dull. But if you come to the PTA range or pulsar timing error range, it becomes a little bit more dull, in the sense that the amount of degeneracy is 2 order of magnitude, but still it is quite good, in the sense that it is very difficult to otherwise probe this mass range of leptogenesis. Okay, so now once again, so I'm going to skip this PTA slide. I guess everybody knows about PTA, that PTA observed these Hellingsdown curves, which is a kind of smoking gun signature for gravitational waves. And in our model with cosmic strings, you cannot fit PTA, because in our model we have stable cosmic strings, which is not favored by the PTA data. But with induced gravitational waves, we can fit our model, but unfortunately, we can fit only with the leptogenesis scale, which is spanning over 2 order of magnitude. So it's quite degenerate. So now we are kind of trying to do a much more rigorous data analysis for PTA for this model. So this is basically the outlook. Okay, so first we want to do now the close modeling for induced gravitational waves, because as I said, we relied on some external perturbations amplitude, scalar perturbation amplitude AS. So we want to generate it from our model, and then we're doing a detailed analysis for PTA, and then we're doing a parameter inference, for example, MCMC computations to assess the quality of signal, in particular focusing on LISA, because in LISA you can have other background, other astrophysical background, for example, background coming from our galaxy, and also extragalactic background. So you need to, you need to do a Fisher analysis or MCMC or Bayesian analysis to assess the quality of signal, whether in LISA your model can be probed or not, or which constraint the future LISA mission can give to our model. Okay, so yeah, so this is basically some preliminary results of our model, that if you have a spectrum like this, then you need to analyze the spectrum in presence of this extragalactic spectrum and also galactic spectrum, and then do a quality analysis of your model. Okay, so with this I would like to conclude that simple leptogenesis model can have all the ingredients to seed an early meta domination, such that it can track the leptogenesis scale, and which is, I think, quite important, because so far, with LEC we can probe the leptogenesis scale only up to TeV, but if it happens at a very high energy scale, then we can do this gravitational wave stuff. And as I showed, that GAD motivated models based on U1 B minus L symmetry, to be specific, is a perfect example of this kind. Then in our work we explored two different consequences of such epoch. First, we studied the gravitational waves generated from cosmic strings and tried to relate the spectral features of cosmic strings with right-handed neutrino masses, or the scale of leptogenesis, and then gravitational wave spectrum induced by the early structure, and we could also relate the peak frequencies of such gravitational waves with the leptogenesis scale. Okay, but once again, the crucial message for this kind of research, or including our work, is these signatures are not as clearly visible. This signature is not the smoking gun signature of leptogenesis, because it's basically cosmic string plus early matter domination, or structure formation of early matter domination. This is the main ingredient. You can basically embed this framework in many other models, but crucially, if you don't observe this signal, including the other models, in our leptogenesis models as well, you can exclude lots of parameter space, including a very large range of leptogenesis scale, only with gravitational wave observations. Okay, so with this, I would like to thank you. And also, if you want to, in case are interested to have like pedagogical write-up, there's a very nice write-up written by a grad student about our work in Astrobyte blog. So you are very much invited to read this very nice write-up about our work. Yeah, thank you. Thanks a lot for your kind attention.
Thank you very much, Roma, for the nice talk. Are there any questions from the audience? Yeah, if not, let me ask a question.
I have one question.
Yeah, sure.
So in your early days, early stage of presentation, you mentioned not only the cosmic strings but also the domain walls.
Yes.
So, but you seems that you haven't mentioned the domain wall role related to the leptogenesis or gravitational wave.
You are right. You are right. I did not. In this presentation, I introduced domain wall just to give an idea about defects. It is not related to the leptogenesis model, but I discussed leptogenesis only with cosmic strings. Yes.
And sometimes I heard that if we have domain wall, they may have some problems with the cosmology.
Yes,
So,
because domain, the energy density of the domain walls, it goes at a to the 2, where a is the scale factor, a to the minus 2, sorry. And whereas on the radiation, it goes at a to the minus 4, right? And therefore, at some point, the domain wall would try to dominate the energy density of the universe, which is catastrophic for cosmology. So for that, you need to destroy these domain walls. So for a standard technique to destroy the domain wall, that you add a very slight bias term to the Z2 symmetric potential so that your domain will get destroyed. Yes, you are correct. I mean, you need to add an bias term to make them annihilate completely. Yes, otherwise they are problematic for cosmology. Yes.
okay, thank you.
Any other questions? I have one actually. So
Yeah, sure.
yeah, in the same. So what would be like the key ingredients, let's say, that you need to make a fully consistent combined induced gravitational wave and primordial black hole analysis?
Yeah, so look, in our model, as I said, what we have, I mean, from the particle physics side, which is leptogenesis in our case, we only have the early matter domination. Okay, but to form a structure, we need some perturbations, right? Because in the large scale structure case, we know we have these perturbations from scale invariant perturbations from inflation and all these things, and we form structures. And similarly, to form these structures at very early stage, we need some external perturbations. Okay, but if you use the standard perturbations from inflation that is basically used to generate large scale structure, you can in principle get gravitational waves, but the amplitude will be very small. What we assume that at smaller scales we have enhanced power in the power spectrum, like like it's a box power spectrum. Like at the CMB scale or large scale structure scale, you have scale invariant, then it goes as like, again, it's a step potential, I mean step function at large k values or small scale values. Yes, so that is the only assumption. But the only problem with this kind of assumption that you can overproduce primordial black holes, because whenever you have a very strong power in the scalar power spectrum, you overproduce primordial black holes. But in our paper we showed that in our case, the parameter space we are working, I mean to obtain observable gravitational waves, we do not overproduce primordial black holes in our case. Yeah, but the key point is AS, or the scalar perturbation amplitude, in our model is a completely free parameter. I mean, we just tuned it to generate gravitational waves. So what would be great if we can generate this AS somehow self-consistently in our model, which we could not do. Yes.
Yeah, I see.
Some very naive question.
Yeah.
So from the leptogenesis, so what are there some easy way to understand the gravitational wave peak frequency? So which was about some or some millihertz or something. So what is the parameter that essentially determines that peak frequency?
This I mean, so I discussed two cases. The first one is cosmic string,
Okay.
and the second one is structure formations. And if you are talking about cosmic strings, so I related this spectral break, where when this plateau will break and then the spectrum will fall. It's basically related when the early matter domination ends or depends on the t end. Okay, so this determines this falling frequencies or the break frequencies. Okay, and but for the peak frequencies, I mean, in this case you get a peak. For the structure formation case, you get a peak. Yes, so here you have peak. Okay, and this peak is basically related to the largest halo you form, uh, I mean, during the end of the matter domination. That is the scale. I mean, it is basically related to that scale. I mean, so it's related to the largest structures that you form in the nonlinear regime of density perturbations. Yes.
Okay, thank you.
Mhm.
Anyone else? If not, let me stop the recording sometimes.